Thank you, Minli. I'm not heading the blood bank yet, but but yeah, managing the part of the research department. Yes, I'm super happy to be here, and it's not a mistake that there's a wrong picture here, but it all started there, and I'm super happy that we are now in South Korea, here in Seoul, to continue this journey, because this is very important that also blood EVs are considered more and more as a drug vehicles, and of course in biomarkers. So super happy to be here, and I just had to take this picture. Sorry, but we were in Helsinki, and it was in a tropic of Helsinki. It is actually this kind of a tropical, how you call them, inside gardens where we had a dinner party, and I was so thrilled to first time meet you, like personally having a good discussions with you, Min, and I hope that in future we can continue this discussion, as I still think what is important to notice that there's no many blood services in the world that are actually doing this kind of a research so thoroughly that we are, and we are not only doing us. For instance, Pia Siljander has been a key collaborator with us because of her long career as a platelet researcher and EV researcher, and of course including all these kind of international collaborator discussions. But I have to say that in a way I'm looking all this field through eyeglasses that are somehow biased by my interest in the respect of the blood service. And contrary that Dr. Dobos was saying that I will probably talk a lot about the engineering and that he doesn't eat my talk, no problem. You didn't, and it was a good that you actually told about those engineering issues, because to be honest, I want to talk you more about before we are going to the engineering. I'm touching, of course, the engineering part, but from the blood service perspective and from the blood and blood cell perspective, we have still a lot of questions of the natural function. And if we don't know the material we start with, why we then do some tricks after that? How do we know what happens after all these engineering if we don't even know the starting point? And I will touch some point of these courageous innovators and companies at the end, because I still think that it's courageous to go forward even not everything is known. We know that from the acetylic salicylic acid, like from aspirin, not everything was known when we started to use it. So, but anyway, we should know maybe a bit better of our starting material than we currently do. So what I would like to say that, first of all, my title, I was a bit afraid because I'm not really an engineering part of the story. And that's why I want to dissect in three parts. First of all, actually, I would like to talk to you about the blood EVs, and because there's no blood EV, there's not existing such a thing than blood EV. It's always coming from somewhere. So the cell is somewhere that is producing the EV. So that already gives me like an uncomfortable feeling. And we also heard that there's also a lot of other things, much more other things in blood in a nanoscale than EVs today. This day has been excellently built. It has been a very, very well built, so that everybody has brought it's like an extra level all the time. Also, that when we are talking about engineering blood EVs for therapeutic usage, it's also like, what therapeutic usage? and we don't necessarily even need to engineer blood EV for the therapeutic usage. And actually, what is the engineering of the blood EV? Sorry, but I'm really wanted that's a last talk, steer the soup a bit, because when we are talking about engineering EVs, we usually think of similar things that we just heard, and that we add something chemically, metabolically, we give some kind of a environment that modify it. But it could be actually just that we engineer it by isolating it differently or activating the cell differently that it's normally done. And that's actually already, to my mind, an engineering in a way, because we change the composition of the EV. And then, of course, when we are thinking about the engineering, we have to think about why we are engineering, what it brings really that we need. And then we are very often thinking about the target cell. And if we're thinking about the target tissue, I don't say we forget, but we don't pay attention too much to the barriers. And that's why I was super happy to hear today about these vessel barriers and like leakage kind of issues that we have, and what is like really like going through barrier, but also going through barrier in the epithelial cells. And that's also one highly important thing that when we're thinking about the end usage of the therapeutic EVs. So as said, there's no such a thing than the blood EV, and that's why my preferential when I'm studying EVs is to first isolate the cell. Well, that's easy. We do that every day in blood service. We isolate from blood red blood cells and platelets and buffy coats. We have the immune cells if so wanted, and we use them for the research purposes at the moment, but we don't actually produce any immune cell EVs as such. But what we are studying heavily is the red blood cell and platelet EVs. And these were all heard today already. So when we are talking about the blood EV, I would like to see more focus on the cell specificity. And also that we understand that we have an asset in blood services to do this, and that actually our bioreactors are the bags that we have, and those bags are differently already routinely done. We have a washed product, we have a small product, we have a larger product, we have a combination products, and all those bags are our bioreactors during the storage already. So that is our bioreactor. And of course, then another dimension that we all know here is that there's no nucleus. It's a good and a bad thing in a way. And that's why, for instance, because there's no nucleus, I'm not going to talk about the modifications that we first transfect and do the gene transfer and make a combination of the RNA with the transporter molecule to the EVs, because if we're not going to the megakaryocytes with red blood cells and platelets, that's quite useless, right? And that's what we are doing. We are producing at the moment these EVs. So then if we are talking about the therapeutic usage, we should then think about, again, what blood cell and its EV could be the best suited for the therapeutic use planned. It's not that we take a red blood cell EV or platelet EV or some kind of a modification of it and can like use it as a general platform, because the starting material is the first step in your engineering. The choice of a starting material is the first engineering step. And said already, like administration route. And that's why we heard today about the penetration through endothelial layers that is varying in a different organs and also based on the healthy or diseased condition. These are the things we need to take into the consideration too. And when we start to understand the composition of the carrier itself, the lipid bilayer as a starting point, and when we understand that the heterogeneity of the pool need to be dissected talked about I have also a picture about like a different EV-sized population from the red blood cell, for instance. So if we are looking at the smaller or larger, then we see the different results. So which one we want to pick up as our engineered vehicle. So in every step, we need to understand what it means. Then I will talk about a little bit about this, like we're talking about the targeting. And I have been evaluating applications where people are developing very fancy engineered products, but they target molecule which they claim is specific for certain cell type. It's far from specific. Actually, it can be dangerously targeted to other organs and other cell types vital for the patient. So why we start to do something that at the end never will gonna succeed? So when we do already in a lab work our fancy development, please let's do it in a way that it has any point in the future for the therapeutic applications. Understand that you can show the point of the technology, but that can be also done with the molecules that are relevant. Because sometimes you just destroy liver endothelium, or you destroy the bone marrow, or what do with the patient after that. And then the robustness of the synthetic particles. They are still there, the synthetic particles. And we have to consider when it's relevant to take the other option and go to the biological EVs, because they are competing with us at the end. So why to do EVs and not, as we have done for a couple of decades, using the synthetic nanoparticles? It was taught about the immunogenic. Yes, the immunogenicity or immune modulation capacity that these EVs can have depending on the different cell types. And again, alone could be the ones that we could use for the therapeutic applications. And yeah, I think I'm repeating a little bit myself, but also we have to think about the uptake already when we are thinking about the start cell. So if you have a large red blood cell EV, even if it's like below 200 nanometers, it's a larger than maybe the platelet EV. It targets and interacts with the target cell differently. It can be like this kind of fusion, it can be like a kiss and run, and it can be uptaken. And then when EV is taken up, we have a lot of synthetic nanoparticles that can be escape from the lysosomal degradation and go to the target effect internally inside the cell. But what do we know actually from the biological membranes and these EVs, how to make them escape from that lysosomal degradation? There is some data already, and there are certain studies, but there's a huge questions that, okay, we can target, maybe penetrate, go to the cell, and what happens after it's taken up? What is the mechanism there? And then again, it might be dependent from the cell it's originating, or actually even so simple thing than the size. So small, if I was talking just like a beginning of last week with the physical chemist who said that why do develop the particle that is bigger than the 10 nanometer? It never go anywhere. So his opinion was this. So do we really understand here what is the size of the EV that goes anywhere? I don't know. I have heard Edith's great talk about that the size matters with the targeting and development. But how many of us has really paid attention to that? Enough, at least. Maybe due to the analytical technologies that gives us a headache. The same time as we are competing with all the other applications, we have to remember that there is an effort, and it might be that instead of competing, we could also join the forces. And we could start to think about what could be the benefit of these kind of hybrid materials that combines synthetic and natural. And then, of course, it's a very, very tempting idea that we have been doing a long time this collecting of blood, separating the cells. We have this allogenic product, personalized product that has been here for a long time. So what is then the hard time to just get a little bit smaller and do the same thing? Well, time are different than when the blood transfusion was invented. Now it's much more regulated. But of course, it is an interesting question when, let's say, blood product regulation turns to the drug regulation side, and we will discuss that also a bit in the coming days. This was the image that was shown, maybe somebody else, at least it was talked, I don't remember, was it Edith or somebody, but we have to keep in mind this. Even when we don't do any additions to the surface or inside or anything, that we understand where we start from. My apologies, this is about the platelets, but the figure here is not about the platelets because I didn't find the picture that I would have liked to find from Pia's something. Sorry. So this is one of my own group's publication, actually the first one that we published, and that was from the mesenchymal stroma cells. It was only to say that it's not only that what is the cell type, but it's then when we go away from red blood cells, it's also like where from the cell. So is it coming from the different internal pools or from the membranes and so forth? So everything then affects. But then again, in platelets, we can also see some kind of nice good things, like you can really tune these cells. You can really make them produce a little bit different contents. And this is something that I hope that I can continue together with Pia to study, because that is something that I feel much more comfortable than doing this kind of hard click chemistry or metabolic labeling or so forth for the EVs. And then, as said, cells can be yin-yang, and they can be good or bad. And that's what we know about the platelets. So what about if we introduce something to the bloodstream, to the patients? Where do we know that it doesn't cause harm or accelerate something that is maybe starting there? And that is actually the question that blood services think. Because we're giving patients for different kind of hemostatic situations platelets, but what about if they have actually like a sleeping cancer there? Can we promote that? And that has been discussed more and more when we have been understanding more and more about the role of platelets also in these kind of negative cycles. Sorry, I would like to go back a few slides, please. This is okay. So that's why we have been having our own adventures. I will just give 1 minute for that, to do these kind of engineered red blood cell EVs. But we have gone like backwards a little bit, few steps, because we realized that we don't even understand our natural EVs from red blood cells enough to go to take that next, like that step. And we have the tools to analyze, and we have the material, so that we feel it's our ethical responsibility for this field to start study more and more this kind of a basic biological things. So we know, somebody mentioned already here, that how platelet and red blood cell EVs are interacting with different immune cells already now. And we already have results with the different macrophages that there's actually very interesting things. We hope we get the paper ready during this year and get it published. And neutrophils are one of the very much of our interest too. But there's not much information on this, as said also Dr. Dobosh. So it's, we actually don't know the basics here, sorry to say. And that's, but that's a good thing. So more research are needed, so just be courageous and do the work. We had the kind of period where we did this kind of fooling around and playing around with our starting material and start to ask the questions like, can we actually target these red blood cell derived EVs, either nanoerythrocytes or naturally produced EVs better, and what could be our approaches. So we have done, first of all, these kind of different tests and approaches with the different kind of methodologies, and nanoerythrosomes were some kind of a tempting idea, because we were thinking that we could maybe load same time when we are producing nanoerythrosomes, and that's what we have been doing. We have tried different kind of, this never published, it never ended anywhere really that would be publishable, I would say, maybe in the future if we have a courage to continue at least some extent. But yeah, just for those who then maybe there's some there in a remote audience or even here that are like puzzling, like what kind of modification there is. So what we have been doing, we have modificating both the lipid membrane polar heads, and we have also studied like a modification of the protein surface of the EVs. It's not easy, it's tricky. Our idea was to do that so that we do first the red blood cells and then do the loading and producing nanoerythrosomes. And because we were not really there yet, it started to be quite heavy. So that was maybe also one triggering aspect that we decided that let's leave this for those who are more experienced and been there longer time, and let's us concentrate to the basic things that also need to be answered. But of course this is very tempting, because then if you have the tools, if you have an efficient system, you can really think about the different applications that you could use. But this also raised my concern then, that was like, okay, we could do this, but is it like a worth of it? Is it like a clever to do this? And especially when we don't know what is the original, how the original EV is working. And I raise really the chapeau for all these courageous innovators in the companies and past and current, who has really tried to move forward, because there's a logic, especially with the red blood cells, even though last speaker, Dr. Dobosh, said that that's why it's not succeeded, but they have the CD47, they should succeed. And of course, all these companies have had their different approaches, and we are just on the journey. These approaches continue to develop, and I'm sure that one day we will see this kind of red blood cell based drug delivery vehicles, either as such or then hybrid. We just need to continue robust work and do the quality checking as has been also discussed here. So this is my take home messages, and my sincere recommendation is that let's start to understand our starting material. Let's start to understand the functionality that we may change, not in a wanted way, when we start to engineer our vesicles, because that is the key question. So thank you very much.